welcome all of you for the week 10 live session for advanced research in smart grid technologies. I'm Gagan Mean and I'm doing PhD in the Electrical Engineering Department with IIT. This will be the agenda for today's session, and we have been following this throughout these sessions. First of all, we will just go through an overview of the material, then we will discuss some questions regarding that material just covered in week 10, and also simultaneously we will discuss some things also. And then we can have your doubts. And in between also, you are free to ask questions. This is deadline for assignment 11 and 12th and 19th. So please submit the assignments before deadline. Recording for these live sessions available on this channel, and also the link is available in the portal. So let us start with the overview of week 10. So week 10, 5 topics we covered. First one, the theoretical portion was discussed in previous weeks. So this was meant for simulation and case studies. So for AC, DC and hybrid AC, DC microgrid simulations were carried out and were shown. And one next topic was parallel operation of inverters in AC microgrid. And then finally, harmonics, effect and mitigation techniques were discussed. So starting with first topic, simulation and case study of AC microgrids. So can anyone of you tell why do we need to carry out these modeling and simulation studies? So we carry out these simulation studies to do rigorous analysis to find out challenges which can be there in implementation. So while simulation we can know if there are some difficulties in implementing that, and also to check beforehand if there are any infeasibilities. These are the two types of studies that can be carried out. So one is the continuous real-time simulation and second is hardware input testing. These software such as this RTDS or OpenRT, they are hardware-based simulation platforms, and they also have associated software with them. So for RTDS, we have RSCAD. For OpenRT, RTLab, it's RTLab. we can simulate our system in RSCAD or RTLab, and that same simulation, that model will be run on the RTDS. On RTDS or Premalata. When we do simulation, we often use this. In general, we use this MATLAB based simulating, or we can also use this Scilab. There are other simulation softwares also. These are offline softwares. When we implement a model, especially when the models are very big, large enough, then when we simulate them, the simulation may take a lot of time, and it also depends upon the time step that we are using. If we use a very small time step in the order of microseconds to do the real-time analysis in these softwares, it will take huge amount of time, because they will use the processing, the computation which is available on our PC or laptop which we are using. So their computational ability is very much dependent upon the system which we are using. So that is why to do real-time analysis, the time step is, we need very small time step, and that requires very good computation ability. So these softwares or hardware, you can say, components, these RTDS and FLRD, they provide us with that capability to perform these faster computations. So that is why I say these are much faster than the offline programs. And that is why these simulators, they can operate in real time as if they will mimic the actual microgrid system because of their fast computation. And as soon as we make some changes in any parameter, we can see how the system is responding in real time. So within 1 or 2 seconds, we will be able to see the change also. Even less than that sometimes. So that is one aspect, that is continuous real-time simulation that we can do. Other thing is we can do hardware in loop testing using these simulators. So they allow us to send output to other hardwares, amplifiers and other kind of processors, and then they can also receive input from those setups, both in analog and digital domains. We can also test real systems such as these power devices and protection equipments using these simulators. So they allow design and operation of microgrid control and also evaluation of protection and power devices before their actual installation. So before we are actually installing that component, we can actually test them in lab using these simulators, so that we can know are there any challenges in actual implementation, or their performance is as per the desired specifications. So then we saw this case study of a simple AC microgrid setup where there is one PV, AC load, and one diesel generator and lithium-ion battery. So can you tell why do we need this diesel generator? Is this required? If it is required, then when? What is the situation when we are going to require this diesel generator? Anyone? So, we have already seen in previous lectures that for any microgrid it can operate in different modes. So there are three modes can be possible. One is grid connected mode and islanded or isolated mode of operation, and the third one is the transitional mode. So either from grid connected to islanded mode or islanded to the grid connected mode. So these three modes are possible. So let us start with the grid connected mode. So in the grid connected mode, what will happen? This microgrid is already connected to the grid, so you can take power from the grid. So when this PV panel will be operating at its maximum power point. It will try to push maximum power, generate maximum power. It will first satisfy the load, and if there is extra generation, then it can charge the battery also. And still, if some power is left, it can even that will not be generally the case. So excess power will be usually stored in the battery itself. When in grid connected mode, if this PV is not there due to whether cloud cover is there or due to in some season the output will be lower than the requirement of load and this battery, then the load can be even fed from the grid. So same is written here. So grid can supply the load when there is no PV, and battery is also discharged. PV always operates at the maximum power point. Since it is grid connected, there is some always even if the battery is fully charged, the grid is always there, so PV can feed it into the grid. So we can always extract maximum power from PV in case of the grid connected mode. And in this case, the battery can charge or discharge based upon the reference signals. Based upon the state of charge of the battery, it can either charge or discharge. Suppose it is already charged, battery is already charged, and this generation is more than load, then it can feed into the grid. So it will depend upon the SOC of the battery, right? And this diesel generator will help in the voltage regulation of this bus. When it is connected to grid, the diesel generator will not be used. It will not produce, it will not supply the load or charge the battery. But in case of isolated mode, this diesel generator will be required, because now the microgrid is no more connected to this main grid, and if the PV output is lower and the requirement of load and even batteries also is charged, then the diesel generator can feed the load. Or the case may be that suppose the PV is only producing 0.2 megawatt, requirement is 0.5. If battery is already charged, it can provide this. If it is discharged, then the generator can provide the load and it will also charge the battery. So in this case, because there is no reference, the grid is not there, so this will provide the voltage and frequency reference. So voltage and frequency regulation both will be carried out by this diesel generator itself. That is why diesel generator will provide this voltage and frequency control, and it will operate in isochronous mode. Can anyone of you tell me what is isochronous mode? We have seen this synchronous machine, right? Synchronous. Syn means same thing. Chronous means the speed. So synchronous speed machine always operate at the synchronous speed. So this is speed and ISO means same. So it operates at same speed because it has to maintain the frequency. And for maintaining frequency is directly related to the speed of the loop. So if you want to maintain frequency, we have to maintain the same speed. That is why it is isochronous. Same and speed. So then here also, here PV may or may not operate in MPPT because it depends upon the SOC, state of charge. If battery is already fully charged, then it will not operate in MPPT mode because it is already charged. So excess energy will be only wasted. So, but if it is not charged, it is discharged battery. There is scope to charge the battery, then it can operate in MPPT. So the SOC of the battery will decide a lot. So when the control strategy will be very much dependent upon this lithium ion battery and its SOC. Is there any doubt up to this point? Doubt. Just move ahead. Now the next is same thing is written here also. So in grid connected mode, if we are in off-peak hours means the load is less. So this what we have written here, this is peak load. So load can be less during suppose the night time, it can be less. So this is off-peak hour. So during off-peak hour, because the load is less and PV is, suppose this PV is operating at MPPT, or it may be during other times, and PV generation is there, the PV will be operating at MPPT and the ESS will charge. The battery storage will charge. And the diesel generator will maintain the voltage of the bus. During peak hours, when demand is high, then the storage can discharge to feed the demand, because here we can see the load is 0.5 peak load and the output of PV is 0.4. So the rest 0.1 has to come from the battery storage. So ES can discharge, rest is, and suppose this is during evening hours. So during evening hours the output of PV will be reduced. It will not be maximum 0.4. It may be lesser. It will still operate at MPPT, try to extract maximum with whatever is available, and then the rest will be provided by the storage. So during off-peak hours it will be charged, and then during peak hours it will discharge. In isolated mode, same thing is happening. One scenario can be when ESS charges, PV is extracting maximum power and charging the ESS, while the diesel generator is maintaining the voltage and frequency, because the grid is not there, and the PV inverter requires the voltage and frequency reference, which will be given by the diesel generator in the isolated mode. Similarly, in other scenario, when ESS is charged, it can discharge because the output of PV is also lesser. Reduced PV output is there. To meet the load, ESS can discharge, And if these two are not able to meet the load, then diesel generator can also support. But it will still maintain, it has to maintain the V&F. So is it okay up to this point? Yes, that is no. So next one is the DC microwave. So here we will talk only about the isolated microwave, because with the present AC system having completely DC microwave, it will not be a feasible option. So we will be having AC-DC hybrid microgrids, and when there is some fault, DC microgrid will be operating in isolation, or there may be some remote islands or villages where these can operate in isolated mode also. So first is the standalone mode. Now, so who can tell me that out of these PV, diesel generator, battery, and supercapacitor, which will require this bidirectional buck boost converter? We have already discussed this at 2-3 times. And this is a very important thing. So this we should always remember after this course is about to end. We should always, at least these things which should be very clear in our mind. So can you answer this one? Which of these sources will be requiring this bidirectional buck boost converter? Jay, can you answer? So it's already even mentioned in the figure also. You can see why the arrows are also already there. This PV will always be feeding power to this DC bus. It will never take power. However, this is unidirectional. Similarly, this diesel generator also is always acting as a generator. Battery can charge or discharge. Similarly, this supercapacitor also can charge and discharge. So we require bidirectional DC-DC buck boost converter for battery and supercapacitor. For diesel generator, we require a control rectifier to feed variable power. If the generation from PV and other these energy storage devices is less than the load requirement, diesel generator can provide that requirement. So we need this to be controlled. So that it has to be a control rectifier. So out of these three, one was critical load and other were non-critical loads. And this was the algorithm for this. So do you have any doubt in this algorithm? Do you want me to explain this algorithm, or we can move ahead? Anyone? So it's clear. Still, let's quickly go through this. So algorithm starts here. It will check. First thing to check is generation, the relation between the load and generation, whether the generation is more than the load or vice versa. So if generation is more than load, then we have to check the status of, then it meet the load. There is no problem. Because we have storage, so we can, because we have storage also, and we are able to meet the load here, so excess, we have excess generation that we can use to charge our storage. So we can charge the storage. And but if the SOC is already reached to its maximum limit, which we have set here as 90, then we will not charge the battery. Battery will be in idle case. But if it is not 90%, then it can be charged. And PV and wind will be extracting maximum power, so that storage can be charged. But if it is already charged, then they will act in regulation mode. Because otherwise, there is no point to extract maximum power. That will simply be wasted. Because storage is already charged, we cannot use that. And this is a standalone case, so we cannot even feed it into the grid. So these two will operate in the regulation. But if the generation is less than load, then we have to supply the load somehow. So we have to see what are the options available to us for supplying the load. We have storage, we have diesel generator for supplying the load. So we check whether diesel generator is available. If it is not available, then we go to battery. If storage is available, we have to check the SOC of storage. If SOC is more, we can supply all the loads. If SOC is 30%, we can, because there are two non-critical loads, we can remove one of them and supply one critical and one non-critical load. But if SOC is still less than 30, then we will only be supplying the critical load. But if the DG is available, then we have to check whether the PL minus PG, the difference is greater than the what DG can supply. If it is true, then it will supply the load and the excess will be used to charge the battery. But if the diesel generator output, the power which it can supply is less than the requirement, then we have to go to storage. Storage has to meet that requirement. Again, the storage will be checked based upon its SOC, number of loads will be supplied. Is it okay? Next one was in this DC microgrid itself. There were two cases. One was standalone, single DC microgrid. Each DC microgrid operating in standalone mode, which we saw in the previous slide. Another option scenario is where two or more DC microgrids are operating in isolated mode and they are interconnected. So here we have seen in the lecture demonstration, we have seen two microgrid interconnection between two DC microgrids. So why do we need this interconnection between two microgrids? Why do we want to do it? How will it be beneficial? Can anyone of you tell why do we need this interconnection? Means how interconnection of two local DC grids will be helpful for the overall system.
Load sharing?
Load sharing, yes, that is possible. So if sorry for the disturbance. Is it visible now? Yes, so one thing is load sharing. So load on one side can be shared by the other one. Because suppose one of the, we have seen in the previous slide also that there are cases when the generation is more than the load. If one of the microgrid is having excess generation while the other is having deficit generation, then this microgrid can provide and power to the second microgrid, and the loads on this one in second microgrid can be supplied. So that is one, that is correct. So any other reason? So that is also, so it increases the reliability. If there was only one microgrid, then this would not have been possible and the load would have to be curtailed. But if we have another microgrid which is excess in generation, then continued supply to the loads is still possible. So this increases reliability. So high reliability. And also you can say if this, so this was how to full screen was this. This is full screen, I think. Full screen option. There is an option in the three, you can see three dots near that end call option. So you can go there and see there is an option of full screen. So high reliability is there, and then so this was deficit in generation, and this was excess in generation. So if they were isolated, then this excess generation would be wasted. Here the load would be curtailed. But if these two are joined, then these solar panels can be utilized more efficiently. So their utilization will increase. So that is also an advantage. So these are one more advantage is that by this interconnection, even if these two microgrids are at different voltage level, we can still connect them. Because one is at 48 volt and other is at 480 volts. Still we can connect them because of this converter. So it's a dual active bridge. Two H bridges are used. This is also called the dual active bridge converter. So DAB. So there is high reliability, supply quality improvement, local energy security. So locally also we are able to supply the load. And connection of grids at two different levels, voltage level. That is also possible. because of this dual electrobridge. Yeah, so this is the dual electrobridge, and it also provides isolation, galvanic isolation. So any fault this side will not propagate here because transformer is there, and it can feed power in both directions. This is a bidirectional converter. The third one was the AC/DC hybrid microgrid. So here we saw different coordinated voltage schemes and voltage regulating devices and their optimal utilization. So if you optimally utilize different these voltage regulating devices, we can increase the reactive power reserve, which is required during this fault period. So if the reserve is high, the post-fault voltage recovery time will be reduced, and we want to reduce that. So strategies should be such that all the devices which are available in the system are optimally utilized. All the voltage regulating devices. So there are different types of voltage regulating devices which are there. Discuss, we will see. So these controlled voltage scheme can be centralized or decentralized. Centralized will always, we have seen in the previous week also, there are three types of control strategies. One is centralized, then decentralized, and then third one. Which one is the third one? Anyone?
Distributed.
Correct, distributed. So which of these two require communication?
Centralized and distributed.
Correct. So here this requires communication, decentralized does not require because it is local. Each of the DC will be having its own controller and they do not know about the others. So here meeting the global objective, it's not possible. But here in these two we have communication and centralized because if one of the link goes out, then the meeting the objective becomes difficult. So that is why it has this disadvantage. But distributed, even one of the link fails, still we can work with the rest of the links because there is communication between the neighboring DJs. Each of one of them is communicating with its neighbor. So that's why distributed is better. So here we have only two schemes, centralized and decentralized, and in the lecture decentralized was discussed because it does not require any communication. So these were the three different states in which the system can operate. So one is the steady state, where in steady state there are only switching of small nodes, very small disturbances, variation you can say, very small. It can exist just as we can see the frequency of Indian grid. So it is never a constant 50 Hz. It is always some small load. We may be switching some of our devices. After a few minutes we switch it off. So these create very small disturbances in the actual frequency of the system. So that is the steady state. And here the requirement or the converters, they can supply less than 40% of Q requirement. and here the voltages will be within the limit between 0.9 to 1.1 per unit. And the second state is this dynamic state where there can be sudden load switching, sudden huge load change in load. So that is dynamic state. Here the requirement in Q is 40%. Here it is less than 40%. So here requirement in Q is more because of the sudden change. We have to mitigate that sudden change, so we need more reactive power. So these arrows shows us the same thing, that in both the cases the voltage will be within the limit, but only thing that changes, that causes this transition from between these two states is the requirement of the Q requirement. If it is less than 40%, the transition will be from this dynamic to the steady state. If it is more, then transition will be there from the steady state to the dynamic state. Then third one is a transient state, which happens during fault. So if there is a 3-phase fault and for 150 seconds, then we require the converters can provide up to 100%. So in this case, for temporarily the voltage will go below 0.9, below the limit, 0.9 per unit. You can see here the voltage is less than 0.9. The Q requirement will be very high here. Similarly, we can go from here to here also. The main thing is this voltage will go below 0.9 because of the fault. Huge dip in voltage. So for quick restoration, for quick recovery of the voltage, we need huge amount of reactive. Then these schemes were discussed, different coordinated voltage scheme. That in lecture 1, the existing schemes have this problem that they give importance to the speed of operation of device. That is the only criteria. They do not check for the operating condition of the device, and all the devices are triggered simultaneously. All the fast and slow acting devices are considered for Q, for providing the reactive power simultaneously. And that leads to inefficient utilization of these devices. So that utilization is not optimal. And the objective of this scheme is to optimally utilize this and also reduce this recovery time. So in this conventional scheme, the reduction in time is possible, but the utilization may not be optimal. So that is why the new scheme was discussed, where there can be more effective utilization of devices, as well as there are some other added advantages like improved voltage profile and improved fault ride-through capability. That is, the device is able to withstand the fault. It is able to ride through the fault. And then the improved transient condition. That is quick restoration of the voltage back to its acceptable level. So there were these 3 stages in this new scheme. First was to identify the operating condition, which was the drawback here. So here first it identifies the operating condition, and based upon that it checks for the availability of device and assign them these 2 roles. Because the second disadvantage was that all of them were considered for providing reactive power. Here it will not be the case. It will first decide which will provide first and which will provide later. So master will provide. So the devices will be divided into these two categories. And then third will be to introduce the time delay for the fast operating devices, so that the slow operating devices can complete their operation and then the fast operating devices will be used. Then the next one was this parallel operation of inverters in the microgrid. So we have seen in UG also, we have seen parallel operation of the transformers and also generators also. So here these are these inverters which are operating as voltage source. Here we are considering two inverters which are operating in parallel, and they are connected to the grid, to the PCC via a LCL filter. This is the inverter output of first and second, and this is the current which they are contributing to the PCC, to the final grid current. So how do we solve this type of network? If you want to find out this transfer function, you want to find out these terms G11, G12, G21, G22. So this is a multi-input, multi-output system. Here we are having two input, two output. Two input are these, and these are the two outputs, I21 and I22. So two inputs are these inverter output for two inverters, and then these are the two inputs, and output are the currents. But the output of one inverter, output current of one inverter is also dependent upon the voltage of the second inverter. That is why we are having this matrix of transfer function. If we have a single isolated inverter, then the transfer function will not be, it will be simply G21 is equals to G11, or if it is between IRAF, so it will be like this. But here we are having these two inverters which are operating in parallel. Both are contributing to this current, and the output of this affects this current also. So they are dependent on each other. Here we discussed two types of current. So do you remember what were those two components of current? So here you can see I21 is G11 V01 plus G12 V02. So here each of the output current of each of the inverter is having two components. So what are these two components? So there were in the lecture they were given two names. So do you recall?
Common and interactive.
Correct. So which one is common here?
Common is which is going to the grid, and interactive in between inverters.
Yes, that is correct. So in this expression, which one will be common? So here we are saying this is I21 is having two components. I21 current is because it depends upon these two voltages, both the inverter output voltages. So if the first component is dependent only on its own voltage, this is the common component, and the second one is dependent upon the second inverter's voltage. So this is because of the interaction between the two inverters. So that is why this is interactive component. Similarly, this for second inverter, there is an interaction between first and second inverter, which is governed by this transfer function G21, and G22 is because of cells. So whenever these type of systems are there, so we represent this by we have studied the superposition principle. Do you remember superposition theorem?
It's not much remembering, but has heard about that.
So let us take a simple. If we have this, if you consider a simple circuit, here also we have two sources, and we want to find. Suppose this is our load. Consider this as load. We want to find the current which is being fed to this load, and we have these are the two sources. So these two sources will be contributing. This IL will be having two components. One due to V01, once this source, one due to this source. We can see it like this. We can divide this current IL into two components, one because of one source, second one because of this second source. What we can do, we can make this calculation in a two-step procedure. First, we can calculate this, considering this is not there. Contribution from second is not there. Then we can consider only the second component, considering that the first source is not there. If we consider that only source 1 is there, so we can short this second source and consider that only first source is present, and then we can find this current. It's very easy because we can know what is this. Suppose these are same, all the resistances are same, then this is R by 2 plus R, so this is 3R by 2. So the current from here will be V01 by 3R by 2, which we can divide by 2 because resistances are same, so it will be V01 by 3R. So IL, this will be, both current will be same, this will also be V01 by 3R. So this is V01 by 3R because of the first source. Similarly, we have to consider second case where first source is not present, it is shorted, and second source is there, V02. Now again we have to do the same thing, but in this case it will come out to be same because the structure is like that. This is R again, it will be R by 2 plus R 3R by 2 current here. Here the current will be again, no, it will not be same, it will depend upon. So V02 is there. The expression is same, but it is dependent on V02. It will come as V02 by 3R. So if V01 and V02 are same, it will be just twice. So is it clear?
Yes, now clear.
Correct. So similarly here also for calculating this G11, G12, G21, G22, we can do that by using superposition. We can consider that one of the sources is not present, short it, and then solve for the ratio. Find out these ratios. I21 divide by V01. We can find out this is shorted, this voltage is there, so we can find out what is I21 in terms of these impedances. and these are connected. That we have to solve, but that is the procedure. Similarly, we can once you short this, next time short this and consider this source and calculate these 4 ratios, and we can find out these 4, and it comes out to be like this. So G11 and G12, because of the symmetric nature of this network itself, these two are symmetrical. That is why this expression comes out to be same for G11, G12. Similarly, G12 and G21 is also similar. And these two are GP and GC are these two functions. So one is not having the grid impedance. This is independent of grid impedance, while this includes the grid impedance. Similarly, this resonant frequency will also be, one is having grid impedance, one is not having grid impedance. That interactive current will not be having the grid impedance. The frequency corresponding to these, the interactive currents, these components will be having high frequency oscillations, and these interactive currents will be in between these two inverters, like this. So the magnitude is same if these values are same. If L11, L12 is same, L21 and L22 are same, C11, C12 are same, then the magnitude of these two current will be same, but they will be cancelling each other. So there will be net. And if this IRF1 and IRF2 are same, and everything, these two are also similar, then there will be no interactive current. They will cancel each other. If this reference is different, then they may not cancel each other. Therefore, the current, this interactive current is so it is proportional to the difference between these references. So if these two references are same, then it will be 0. While the common current, that it is proportional to the sum of the two. So that is the current which we want to feed into the grid. Is it clear?
Yes, yes.
So let us move to the last topic, which is the harmonics, effect and mitigation strategies. So harmonic is one of the type of power quality issues. There are several power quality issues which can be broadly classified into voltage related and current related. And in voltage related we have sag, voltage swell, and voltage interruption. And in current related, harmonics, notches, transient and unbalanced load. And this harmonics is the topic. What are the causes of harmonics? Can you tell? Can you mention any? Why do we have harmonics in system? What are the major causes or components which result into these harmonics, which feed harmonics into the grid, or which draw harmonic current?
Many active devices such as power converters.
And so, can you tell why these active devices they draw this? What is the main reason for them to draw or inject these harmonic currents? What is the basic reason?
Switching, due to
Correct.
switching.
Correct. So what happens due to switching?
Switching.
It is correct. Switching is correct because switching is distorting the current waveform.
Yeah.
That is why we want to go for the switching frequency. We want to be very high.
Yeah.
As if switching frequency is high, and yes,
frequency wise, then effect will be less.
yeah. we can, and also depending upon the modulation schemes, we can eliminate. There are certain modulation schemes which help us eliminate these harmonics inherently. The main reason is switching, correct, and those are the main. The switching is also the main reason for this power factor. Also, they do not operate at unity PS because of the lag between this delay which is created between the voltage and current.
What is the difference between voltage sag and swell? These two terms.
Yes,
what significance?
So swell means it's a general term. If we go by literal meaning also, swell means if something is increasing.
Okay.
So and sag means it is reducing. So we study this between two transmission tower. There is a sag. The wire is sagging.
Yeah, sag.
So this is called sag. This is called sag. That is when normal, if we consider this as normal position, so from normal position it is sagging. Similarly, if we talk about swell, then this will represent swell. It's just representation to explain. This is not the actual. This will never happen in transmission towers. But so similarly in voltage also, if this is the regular voltage level, normal voltage level, but for certain duration, for certain number of cycles, if there is a continued reduction in the voltage magnitude RMS, suppose this so this happens. If it happens for certain number of, are some standards which govern this, how much for how many cycles, if the voltage is less than 0.9 per unit for certain number of cycles, then it is termed as voltage sag. So this will be voltage sag. So permanent, not a temporary reduction in the RMS value for a particular duration of time, and it will be termed as voltage sag. Similarly, if there is an increase in voltage beyond 1.1 per unit, then it will be termed as voltage swell.
Okay, right.
So that is true. Correct. Harmonics are introduced by these power electronic devices. Even the saturation in these, the cores that we use, the transformers. If the core saturates, then that can also introduce harmonics. These motors also, they also introduce, these machines also introduce harmonics. There are slot harmonics and other types of harmonics. So they also introduce harmonics. So the effect of these harmonics is that in motors and transformer it can result in heating and losses, and then there can be interference with the telecommunication lines. So mostly this 9th to 21st harmonic, they have adverse impact on these telecommunication lines. So they have severe interference. Then there can be error in these metering and control circuits also because of these harmonics. So these are the pictorial representation of all the kinds of these power quality issues. So this is the normal voltage. Here we see there is a temporary reduction in RMS value of voltage for a certain duration or certain number of cycles, or almost 2.5 cycles. So this is a voltage sag. The second one shows voltage swell. So there is an increase in voltage for few cycles. Here there is an interruption. There is no voltage. So there is an interruption, and this can be because of, and this can voltage dips mostly in fault. It becomes almost near to zero. So then for current related or quality issue, this is ideal current. This will happen for the non-linear loads. This is example of notch, high frequency current component. Here also you can see these are notches, high frequency current component. So we have this. I see the right? Is this correct? Yes. So if there is a huge change in voltage, then there will be high changes. There will be high values of the current will shoot. That can happen because of switching. And this is unbalanced load. Different phases are having different currents, different loading. This can happen. And in distribution system, we generally have unbalanced loading. Then this is harmonics. Different frequency components are available, except in addition to the fundamental. And this one of the phase is not supplying the load. So these are different current related power quality issues. Then we discuss different techniques for mitigation of these power quality issues. The first one is the passive filters. Then in passive filters we can have series, shunt or hybrid. If we see these two are shunt, these two are series, and then we can have their hybrid combination also. So passive filters are the most widely used ones. And in high voltage transmission system we use them because of their low cost, their simplicity, and their ability to provide reactive power compensation. And they are also extensively used in distribution system for improving voltage profile, for power factor correction, and then for reducing losses, and neutral current compensation for load balancing, and battery utilization of electrical equipment. So if this passive, they are able to provide so many advantages, then why are we going to active filters? Anyone? Can any of you tell? Why do we need active filters if passive also does so many things? They are also cheaper, low cost, simple to implement. And why are we going for active filters?
They are heavy, bulky. Second, passive filters are
okay.
They are bulky, heavy, capacitor, inductors, big capacitors. It is one of the reason, and they are having limitation in harmonic filtration. They cannot cater higher order harmonics. Very rare. Maybe initial fundamental frequencies and
that can be done. can do that also. Using this passive filter also can do that. There are some other limitations also. So one thing is that they are, once we have designed them, we cannot change.
Okay.
If there is some change in the system system, then their tuning will be affected. They are tuned for a particular frequency. We cannot change that continuously, because once their LC values are fixed, or they may have some steps. Generally, we don't have a single L or single fixed capacitor. We will be having several units, so we can have step change in step, but in between step we cannot do anything. So for that, the filters are not tuned. And if system changes and the filter is not tuned for that particular operation, then it will lead to distortion.
Yes, sir. That is the main reason. But
yes, they are not able to adapt to the changing system requirements. That is the main problem.
yeah,
And then it may result in overcompensation. So we have to make them adaptive in nature. Active filters will be are required. So we can change them, tune them continually. They can change their settings with system. They can adapt themselves with the changing system. So the adaptive filters can be three types. Can be of three types. One is shunt, series, and here also same shunt plus series. So this UPQC can provide both the functions. It can do both the functions. Shunt filter can provide. These will be shunt for current compensation. This will be for voltage. So these are called dynamic voltage restorer, series 1, and this is DStatCom, static compensator. And the UPQC can perform both the functions of shunt and series. So this was the demonstration which was shown. So here this grid side filter, this is acting as shunt or series. Based upon this, you can see how this is arranged, how this is connected. Because this is connected in series with this line. This is series. Here, this is connected in shunt. It is not in series with this line. So now can you tell which type of compensation is this? Or grid side converter or load side? Is this series or shunt?
series, right?
Correct. So this is series, so it will provide high impedance path for the, so it will block the harmonic currents. So that will not be able to flow through the line. Similarly, this is shunt and this will provide a low path. So they will flow through this path and they will not be able to enter into the line. That way, this is free from harmonics. So from here we are blocking and from here we are removing. And this LC filter is used to reduce the switching harmonics of this current. Correct? Is it okay? So, is there any doubt up to this point, or in week 10 material?
Please explain some more about LC filters as just in the previous slide. Harmonic part.
So just as we have these, we discussed this one, right? These LCL filters. So here also we are having these resonant frequencies. So we tune these filters. All the filters does the same thing, but they offer different degree of compensation or filtering, the harmonic filtering. So they will be tuned for a particular frequency. So based upon the system requirement, we will tune the filter. But LC filter is a first order filter. And LCL is second order. This is also much easier to implement. That is why here we are not using LCL. Here even LCL will also work. Oh, sorry, LC will also work. So when this converter is switching, so because of switching, it will generate some harmonics. And if we are able to reduce that harmonic, then the quality of current which is being fed here, it will be good. Is it okay? Jay?
Yes, okay. These distortions
Yes.
affects current as well, voltage waveforms also. They are only current part.
Yes, it can be there in both.
Both, no?
Yes. So in the lecture, I have not shown waveform here, but in the lecture, the waveforms, they were having distortion in both voltage and current. It depends upon the entire system, which will be having more. I think there is some noise from your side.
No problem, okay.
So, are there any more doubts?
No, please
So
record the
then
question.
let us go through questions then. So this is the first question. So all the questions are mostly based upon what we have discussed, so you must be able to answer all these. The purpose of microgrid modeling and simulation are. So this is the first thing which we discussed today. The first option is conducting rigorous analysis, then identify key challenges in implementation, then feasible solution before actual physical implementation, or none of the above. Which one is correct? So which one is correct?
B and C both.
Why not A?
It's not rigorous analysis.
Regress analysis here means that we can do, suppose we want to model a particular microgrid, and this we want to implement in reality. We want to implement this microgrid, but before implementation we always do simulation studies, which is helpful in simulating all the different types of cases which may happen in actual. So this simulation allows us to simulate all the different types of scenarios. So that rigorous analysis here means that kind of analysis where we can consider each and every possibility, or if not each and every, at least maximum number of scenarios we can try to analyze before the actual implementation, so that we can see how it will behave in real life. So here rigorous is not that rigorous mathematical analysis or that kind of. It means in terms of the number of possible cases that we can simulate, number of possible scenarios we can observe, analyze.
In that sense, okay.
Because when we want to install a system, the system should be able to work for all different kind of conditions, situations. So if we are installing a system and it operates only for one condition and it is not operating for several others, then it will not be a good system. So to ensure that it works well for most of the conditions, we have to do this kind of analysis. So option A, B, C, all are correct. So next question is, identify the incorrect statements with regards to inverter control of PV and storage in microgrid. So first option is PV and storage controls are based upon decoupled PQ control strategy. Second is PV and batteries sources are interfaced to AC grid using dynamic average model of the voltage source converters. Then third is dynamic model represent high switching frequency dynamics. And last is these models allow higher simulation time steps for modeling large microgrid cases. So which one is correct? Oh, incorrect is asked. Which one is incorrect? We have seen in the previous lectures, previous weeks, how do we achieve this decoupling between P and Q? So this decoupled PQ strategy, how do we do this? There was one question in assignment 10 also. First question, I think. Not directly related to this, but it is used for developing the decoupled PQ control strategy. We use this aux transformation, ABC to DQ frame transformation, and in DQ frame these two are decoupled. which is also achieved by properly selecting that theta for DQ frame, and that is done using the PL. So is the first option correct? PV and storage controls are based upon decoupled PQ control strategy.
Yes, correct.
Yes, this is correct. What about second? These sources are interfaced using dynamic model of voltage source converters. Dynamic average model. So are there any other models?
Incorrect.
Seems to be correct.
No, incorrect.
Why? Why incorrect?
Other model is also dynamic average model.
So is there any other model also available for modeling these voltage source converters? So there are two models. One is this average model, and then second is switching model.
Yes.
This will be governed by this the modulation index. This will be mainly determined by the duty cycle. This will give the transient behavior cannot be captured very well by this average model. The output will look like something like this. Even if transient is there, it will after transient it will settle like this. But in switching, we will not find this type of output. We will find something like this because of switching frequency. So high frequency component will be there. Here it will not be there in average model. It will average out all the frequency components. And the simulation that we do depends upon the frequency components available in the system. If we have several frequency components, the time step has to be such that, and if you want to see the entire behavior of the system consisting of all the frequencies, then the time step has to be determined by the highest frequency. So highest frequency will result in a lowest time step. And if the microgrid example is setup is very large and highest frequency component is very large, then this time step will be very small. Suppose it is in milliseconds and we want to simulate a very big microgrid system, then doing simulation at a very small time step, it will be very computationally expensive. It will take a lot of time to simulate. So that is why we go for average model. So average model can be simulated with larger time step also. So large microgrid cases can be solved with higher simulation time step with this dynamic average models. So if we are not concerned much about the transient behavior, we can use this dynamic average model. It can capture the steady state behavior very well. Is it okay?
Okay.
So which options now? Can you tell which all options are correct here? Incorrect. You have to tell the incorrect option.
Incorrect.
Which one is incorrect here?
B is also correct.
B is
B
correct.
is,
B is also correct. D is also correct. What about
B is
C?
also correct.
C. So, dynamic average model represent high frequency dynamics. Is it correct?
No.
No, not correct, because
Yes.
that is that.
Yeah.
For that we have to use the switching model. High frequency dynamics means transient behavior we cannot study using average model.
Yes.
C is incorrect.
Yes.
So when we model these inverters, we have to decide. We have to choose which type of model we want to make. Switching model or average model. That reference which I had shared in the last week, in same
Yes.
book you can use for this also, for studying this, and that book is specially meant for this design of voltage source converter. These things are explained very nicely in that book and in very great detail. So entire first or second chapter are on this. Entire chapter is on average model, so you can go through if you require. Then next question is function of diesel generator in AC microgrid. This also we discussed in the beginning of today's lectures. So which one is correct? Frequency regulation by changing mechanical input. Terminal voltage regulation by varying field current. And third is normally excited generator operates at 0.8 power factor. So which one is or are the functions of diesel generator? Who would like to answer this? Sunil, can you answer?
All of answer A, B, both are correct, but C.
Correct. A, B are correct. So when the diesel generator will be providing voltage and frequency regulation in grid connected mode or in the isolated mode?
Isolated mode.
Correct.
Yes.
In grid connected mode, it will only maintain the voltage regulation.
Yes.
Bus voltage. Because in isolated, there is no other source. PV also require a reference, so diesel generator will provide that voltage and frequency reference. C is not correct. For an overexcited generator, it will provide Q. It will inject Q. For underexcited, it will absorb Q. But for normally excited, it will operate at UPF, unity power factor. So this point at is not correct. It should be unity PF. Next one is which statement is which of the following statement are correct with regards to inter-DC power flow? So this is for the isolated case of DC microgrids when there is an interconnection between two microgrids. Then there will be inter-DC power flow. We have to choose correct options. Effective control and coordination is achieved without communication.
Answer B.
Answer B. So several other state. This is not. This is a multiple choice. More than one statements are also can be correct. So this is
A and B.
A is correct. Effective because we talked about decentralized control. This is correct, and that does not require any communication. Then high control complexity. No, because if A is correct, B cannot be correct because A does not require any communication, but centralized will require a communication. So either of the two will be correct. But we have already discussed that it is a decentralized approach. So B is not correct. And this is also not, the control complexity is not high. It is less. That is why we are using it. Because it is decentralized. Decentralized will be the simplest scheme. So control complexity will not be much. Then what about C? Isolation is not provided. Is it true? Consider these two grids are interconnected. How are we interconnecting them? We discussed this few slides back. How are we connecting these two microgrids? There are two microgrids. In between we are having one dual active bridge converter, right? And it's a bidirectional. So there are two converter, two H bridge are there and which are connected by a galvanic isolation. So isolation is also there. So this is also not correct. What about D?
Actually, it is high reliability.
Yes. So option A and A is only correct. D is also not correct. This is high reliability and also it takes care of extreme scenarios. So I have clubbed these two. Here also I have clubbed two options. So only option A is correct. Yes. Next question is, which of the following are voltage regulating devices? We saw different types of devices. Active
OLTC and
OLTC is correct. Statcom is correct. What about DC microgrid?
It's a grid, it's not voltage control.
But using DC microgrid also we can. Oh, I have written devices here. So.
Yeah.
So it is not a single device, it's a collection of devices. Correct. Either I have to change this or I have to change this option.
Actually, in microgrid, we will have OLTC and Statcom.
Correct. So, in one sense, these two are a subset of this.
Yeah.
So, I will change this itself. So this, all of the above is correct. Next is what is the question is which of the following is true regarding the interactive currents?
A and B.
It is current component with high frequency oscillation, that is correct. It flows between the two inverters, that is also correct. And frequency of oscillation is twice the frequency, so this is not correct, right? What will be the frequency?
Equal.
The resonance frequency.
Is it equal to resonance frequency?
Correct. This will be this. I have made it twice. It will be same as the frequency, resonance frequency of the LCL filter. And what about the common current? The common current. What is the main function of common current?
It flows to the grid.
Yes, it is. Its main. It is the. Its main contribution is to supply power to the grid.
No.
Yes.
So I have one doubt here.
Yes.
Actually, in one of the question number 10th assignment, I am not convinced with that answer.
Yes, it should be, because if everything is similar, yes, it was even in lecture. It was mentioned that if they are similar, because here also we have seen the expression for the transfer functions here. This is same.
Yeah, exactly. Same magnitude in opposite direction. Opposite. Out of phase.
Yes. So here G12 and G21 are same.
Yeah.
And they are similar, so even this GP will be same. So that answer has to change. Yeah, someone had also posted it in the discussion forum. This is okay. Next question is select the correct option for parallel operation of two inverters in microgrid. For parallel operation of two inverters. First is common current is responsible for feeding power into the grid.
Correct.
This is correct. Common current is proportional to the difference between reference currents.
No.
This is not correct
Not
because
correct.
it is proportional to sum of the references, not difference. The difference for the interactive current is proportional to the difference between the two currents. Then C is interactive current of an inverter is sum of two components. Is it correct? You can see this.
No,
Yes.
is correct. Interactive current of an inverter.
Yes. Both interactive and common current are sum of two components. Yeah, I think it should not be like this. Say correct. They are both of them are sum of two components because we have
That is correct.
this is these are two terms. One is difference, one is sum. So both are having two terms. This is also correct. And then problem of interactive current and common resonance does not occur in L filtered inverters. I made a mistake before. LC will not be a single first order. LC is not a first order. L is a first order inverter. Sorry for that. Yes, problem of interactive current and common resonance does not occur in L filter inverter. This is also correct. This resonance will happen when there are two energy storing elements. Correct? It will happen when L and C both are there. But here we are having only one energy storing component, which is an inductor. The resonance phenomena is not there. Is it okay? So option A and A, C and D, these three are correct. Next question is, this is easy question. Which of the following is there are current related power permutation?
Harmonics and notches.
What about this?
It's also there.
This is outrightly incorrect because voltage. This is also correct.
Okay.
Because unbalanced load will also distort the current. Because we are seeing here, it will result into this kind of output.
Okay.
The unbalance will result in negative sequence components, negative sequence current, which are also they are also not good for loads, especially these motor loads. Negative sequence will result in overheating, torsional stress also. Mostly this torsional stress that will create stress on the rotor. So these are not desirable. So it is always desired. It is desired to have this unbalance as low as possible. There are some standards which determine how much unbalance is permissible. So mostly I think it's less than 2%. And this one, next question is this. Disadvantages of passive filter is there are. Large size is required and causes overcompensation. Change in system retunes the filter and causes distortion. And it is adaptable to varying system conditions. Which one is disadvantage? So which option is correct? Passive is not adaptable.
A, B.
Yes, AB is correct. Because it is not adaptable. Therefore we go for active. So this option is neither its advantage nor disadvantage. So here we are correct. So these are the questions. Are there any other doubts? Which you can try to do by do yourself. Try to derive these expressions. It will be good. It will be a good exercise. Just as we did we solved this simple circuit. Similarly, we can also solve this. Also, it will be a little bit time-taking process because so many components are involved and these two are circuit is big. There are 3 loops. Solving this will take time, but it will be a good exercise. You can try to see whether you are getting these expressions. This principle is used several times. Many places we use this superposition theorem.
I think it is a Norton theorem, basic electrical engineering.
Yes, Norton and Thevenin's. Those two are
Thevenin's, yes.
equivalent. If we have a network, complicated network, and we want to represent it, then it can be either represented as a source in series with the impedance or as a current source in parallel with an impedance. So we call it as Norton impedance, and this is the Thevenin impedance. Thevenin voltage, Thevenin impedance, and Norton current and Norton impedance. So this we studied. These are the basic theorems which we use several times. And superposition was also one of those theorems. While calculating that Thevenin impedance, we use that concept. And if voltage source is there, use the current source. And if you want to calculate Thevenin impedance here, then we have to replace all the sources by their impedance. So this will be shorted and this will be open. So this is gone. If this is R and this is R, so Thevenin impedance becomes L/2. So is there any other doubt?
Passive filters are not very adaptive. If they do overcompensation, then what will be the harm to the grid and what they can create problems?
It's overcompensation.
Yeah, overcompensation. Drawbacks of overcompensation. I mean,
I am not able to recall this. Remember, drawbacks were problem can be
that's one thing. Maybe over voltage. I think.
yeah, that can happen. Over voltage, under voltage problem can happen because of overcompensation.
Over voltage can.
That is a problem.
Apart from that, we'll discuss in next part. I'll also try to.
We'll be injecting more reactive power into the grid.
Yes, that is correct. If
Actually, we are having some problems. Same thing, we have passive filters in our system. Sometimes when the grid voltage is at higher level, and we are also injecting reactive power, and the power factor goes to minus.
No, what's the harm to our equipments? I mean to say.
If voltage, yes, continue.
If you don't have protection system at LT, and LT transformers always we are using in half grid. Matlab means power transformer we will have OLTC. So online it will change, but offline we cannot change. Online we cannot change for the distributors transformers. So there will be effect to the equipment. It will shoot up the voltage.
Yes, and then equipment will be damaged.
Yeah, exactly.
Especially these power, right? Nowadays we use all these electronic equipments. They are powered.
We are facing many problems with lighting system. See, there won't be any control over lighting system, and when the voltage terminals, if it shoots up, and same time these passive filters, capacitor banks, are injecting more reactive power to grid. There won't be any control over the lighting.
Right. It will further exacerbate the problem. Over voltage was there, and if overcompensation is there, they will further increase the voltage, and then all the equipment will be damaged.
Still, we have active filters, APFCs in LT system, but it cannot control.
Yes, that is correct. This is a common problem in these low voltage distribution systems, especially in remote areas, in outskirts of cities. The problem of over voltage is there. Several these SMPS, they are damaged because of over voltage. That is a good example. Thank you.
Yeah, this is my primary observation.
That is
since we are dealing many years. But there is no other solution at 6.6 kV and 11 kV. So we will have to go for passive filters.
We are not using these voltage regulators in distribution system. If we use that, that is one of the solutions. In India, we are not using that. They work on line drop compensation.
Sometimes we are running our motors ideally to compensate this.
Yes, that is. You have good experience in this area. You are actually saying these things. So that is good. So let us wind up then today's session.
Yes, okay.
Thank you.
Thank you.
Joining.
Thank you.
Yes. So only 2 sessions are left. So we'll complete these two in the upcoming 2 weeks. So will you be giving the exams?
Yeah, definitely.
Good.
Okay, we need some information on exam pattern.
It will be.
It is descriptive or
no? It's MCQ.
It's
same as assignment.
Same as.
Yes,
and how many questions will be there, and what is the timing?
That even I have to ask. I will ask the coordinators.
Okay. Because if we get clarification and we don't know the time duration also.
I think before the exam, the instructions also will be released. The duration of exam. Number of questions may not be there, but duration will still be mentioned. Still, I will check it out and tell you in the next class.
Today we got one mail regarding examination pattern.
Okay, what was
Whether
that?
it is computer based or paper based or computer. But there is no clarity how many questions and what is the duration.
The number of questions, I think it will not be mentioned, but duration, that might be mentioned. I will check it. So thank you. Let us meet next week.
Sure.
Thank you.
Okay.
Night session.
Thank you.